Namaskar friends, myself Dr. Ashwini Kumar Gupta. Today we'll be continuing our lecture series of this basic organic chemistry. If you remember in the past lecture, I had taught you the topic called isomerism, in which we had done structural isomerism, then what is structural isomerism, which is also known as constitutional isomerism. In structural isomerism, we have chain isomerism, positional isomerism, functional isomerism, ring chain isomerism, and metamerism. Up till now, that much we have done. And one more branch of isomerism is stereoisomerism, which we'll do it later on. But one very important topic of in structural isomerism, which up till now we have done positional, functional, ring chain, metamerism. The another important topic left is tautomerism. Now, what do you mean by tautomerism? So today we will start with tautomerism. I hope you might have understood the previous lectures, okay, and you have done a revision of it. Prior to starting the lecture, I will just request you to just like my video, and please do share with your like-minded friends and your known ones so that they can also take the opportunity to go through this lecture and easily they can understand. Okay, so I request you to please do like and share it, and try to, and please subscribe my channel so that you can get my video intimation of my videos in the future. Fine, so we'll start with tautomerism. Tautomerisms are structural isomers in which those isomers they differ in the position of atoms due to the migration of alpha hydrogen atom or acidic hydrogen atom. Alpha hydrogen atom or acidic hydrogen atom. Take for example, first of all, what do you mean by acidic hydrogen atom, or also it is known as alpha hydrogen atom? Alpha hydrogen atom. Alpha hydrogen atom is also known as acidic hydrogen atom. Acidic hydrogen atom. Basically, it means the hydrogen atoms which are placed next to hydrogen atom, immediate next to or electronegative group. Fine. Take for instance CH3 C double bond O OH. This is a electronegative group. And this hydrogen atom, these hydrogen atoms, this is known as an alpha hydrogen atom. So because alpha carbon atoms are alpha, these are acidic hydrogen atom. These are acidic hydrogen atom. Similarly, I will take CH. Suppose I can also write it like that, CH2 CH. Take for example, you can also say, take for example, a ketone. CH3 C double. So this hydrogen also is an alpha hydrogen atom. Similarly, these hydrogens are also alpha hydrogen atom. This. So this is this. So these are acidic. So it is the shifting. It is the shifting of these alpha hydrogen atoms. CH2 CH3. Suppose if I do the shifting of this bond, fine. This will be CH2 double bond C O minus dash CH3, because once it goes here, then this has to go here, and immediately the hydrogen atom which will be released, it will be absorbed by O minus. So it will be CH2 double bond C OH CH3. Right? That means I can write CH2 double bond C OH CH3. Right? Similarly, I will take another example. Take for example, if I take CH3 C double bond O, and this is S. This is nothing else but acetaldehyde. This is nothing else but acetaldehyde. Acetaldehyde also it can be written as, so CH2 dash H dash C double bond O dash H. Fine. So this will become CH2 double bond C OH and H. Fine. This is the vinyl carbon atom, so this is vinyl alcohol, and this is acetaldehyde. Fine. So have you understood what is tautomerism? Tautomerisms are nothing else but they are structural. They are part of structural isomerism, in which there is a the isomers, they differ in the position of atoms. They differ in the position of atoms. The position of atom means hydrogen is one of the atom. The position of this hydrogen atom differs and it goes to the oxygen atom. That means this acidic hydrogen atom shifts to O, right? So these two isomers are formed. This is one of the isomer, this is one of the isomer. Similarly, this is one of the isomer, this is one of the isomer. So the shifting of acidic hydrogen atom forms two isomers. These are two isomers and these are interconvertible. To be more precise, they are interconvertible. What do you mean by interconvertible? Interconvertible means one form can be converted to the previous form and the previous can be converted to the second form, right? Similarly, suppose take for example this is B and this is A. This we can write like that, right? OH. This can also be written as, it can form like that, right? Then it will become again CH3 C and then double bond O, and this. Again same thing, it is A, acetaldehyde. So that means they are interconvertible, right? That means they are interconvertible. So I think so you might have understood what you mean by tautomerism, right? Now there are different types of tautomerism. First one is known as dyad system, D-I-A-D, dyad system, right? What do you mean by dyad system? In this, there is a shifting of hydrogen atom, that means acidic hydrogen atom, from one atom to the next atom, to the immediate atom. Hydrogen atom is shifting from atom number 1 to atom number 2, is known as dyad system. For example, that means I will say acidic hydrogen atom shifts from atom 1 to next atom 2. Fine. Take for example right, no doubt this is it is an acidic hydrogen atom. So suppose if this is the second atom, right? So now what will happen? This has a lone pair of electron. This will pull the electron towards itself and it will form C triple bond N H. C triple bond NH. So now since C has lost the electron, right? C has regained its electron, because so it will become minus charge and will become positive charge because its valency also has increased. Okay, समझा? So the valency has increased and the valency has decreased. So this is minus charge and this. So this is known as cyanide group, and this is known as the isocyanide group, right? This is known as the isocyanide group. Now The second one is triad system. I hope you have understood what you mean by the dyad system. Dyad system means from atom number 1 to atom number 2, and in triad system, in this what happens, the migration of hydrogen atom. Same thing. Hydrogen atom means acidic hydrogen atom from atom 1 to atom 3. It was previously it was atom 1 to atom 2, now it is atom 1 to atom 3. The best example for this had happened to be known as keto-enol tautomerism. Take for example CH2 C double bond O. We can take for example OH. Okay. So now this is, it will go here. So it will be CH2 double bond C OH, COH and OH. That means if this is atom number 1, this is atom number 2, this is atom number 3. So from first atom to second atom, right? From first atom, similarly we can take as ketone. It will form CH2 double bond C dash OH dash CH3. That is this acidic hydrogen atom from 1 to 3, the third atom. So, okay. Similarly, if I want to take this aldehyde, this will go here, this will go here. So it will happen CH2 double bond C dash OH and dash H, right? This is vinyl alcohol. So this is known as triad system. Yeah. Now, in triad system we have seen what is tautomerism. Now, generally what happens? So, CH3 dash C double bond O CH3, which gives me CH2 double bond C OH CH3. Fine. Now this is 99.9% is the, and this is hardly 0.1% is the existence, you mean to say, right? So the stability is more towards this and less towards this. So forget this. Stability is more towards this and lesser towards this. So this is highly stable as compared to this. The compound, so the ketone precisely wants to stay in this particular system only. Now issue comes, so what, why? Because the C double bond O, one more example, prior going to that reason I'll tell you. Take for example this, right? This is known as cyclohexanone, right? Suppose if I write like that, no. Fine. Now, this is again approximately, you can say 99%, and this is approximately 1%. But why? Now, why? Because the C double bond O bond is much stronger than COH bond, right? So C double bond O, thus the keto form predominates. predominates. Why? Since C double bond O bond stronger than COH. Fine? Yeah. O are also stronger than not only COH but also C double bond C. C double bond C. You can see. So C double bond, sorry, C double bond C or C single bond OH, C single bond OH or C double bond C. This one. Yeah. Now, there are few examples where the C keto form does not predominate. Rather, enol form predominates. Take for example this. Fine. Now, in this, it so happens, you can see like that. Similarly here, this form is this. Now, how come this hydrogen is there? So this will go here. Fine. This, and this will be OH. Right? This is a phenol. Now, why does enol form? This basically is much more higher, 99.9 you can see, and this is hardly 0.1%. So this phenol predominates over this structure, you can see, right? That means suppose this is A, this is B. B more than A. Why? Since in B there is a aromaticity. That means phenols are aromatic in nature and aromatic compounds are highly stable. These are non-aromatic. They are not aromatic. That means there is no conjugation. Double bond, single bond, double bond, single bond, as you know. So aromaticity or conjugation, you can say. So phenol predominates. CH 3C double bond O dash CH. Take for example, this is nothing else but it's a dione, right? Pentane dione. Okay. So I suppose if I take this, so this will be CH3C OH double bond CH dash OCH3, right? Why? Because if this is single, double, again single, that means conjugation. So single, double, single, conjugate, right? So this will be predominant. It predominates normally 92 to something 94% is diketone, and the remaining part is 92 to 94% is all form, and this is hardly 3 to 4% something. 6%, 3 to 6% happens to be a diketone, right? So the predominant formation is resonance, and immediately resonance will be due to resonance. Again, this OH will go here, this will go here, right? That means we can see it is also known as resonance. That means this hydrogen atom will go here and here. Again, this hydrogen atom will come here, and then this is so this is resonance or conjugation. Therefore, this is formed. Now, there is another type of, after triad system, the third type of tautomerism is known as nitro and acinitro system. nitro and acinitro system. Okay? Now, what do you mean by nitro? Nitro group, we know CH3 and double bond O, single bond O minus with a positive charge, right? It is written like that. It is written like that, right? Now, suppose, or we can say to be more precise, CH2 and here H, right? Or I will just write it much more clearer. Okay, so it will go here and this will go here. CH2 double bond and single bond O H, you can say, and this is OH, right? This is known as the nitro and this is known as acinitro. Nitro and acinitro. Here basically it is an equivalent, right? Nitro and acinitro. Now, after nitro acinitro, the last, the second last happens to be nitroso and isonitro. Isonitro system. Dyad system, triad system, nitro acinitro and nitroso acinitro. Now, what do you mean by nitroso? CH3 CH2 dash N double bond O, right? N double bond. This is nitroso. This is nitroso, right? Now, so I will say CH3 dash CH double bond NOH. Fine. This H will go here and then over. This is known as isonitroso. That means the shifting of hydrogen atom to the third atom. 1, 2, 3. So CH2, this is nitroso, NO is known as nitroso, and this is isonitroso, right? Now the last system is imine, enamine system. Imine, enamine system. Now what do you mean by imine? Imine means speaking CH3, CH2, CH double bond NH. CH double bond NH. This system is known as imine system. Always remember. C double bond N. C double bond N. CH and double bond N is known as the imine. Right? Now it will form CH3 CH double bond, sorry, CH3 CH double bond CH single bond NH2, right? CH, this is the, it will go here and then, right? This is the imine, this is the acidic hydrogen atom, right? So this is enamine. Enamine is what? C double bond C bonded to an N. C double bond C bonded to an N is known as enamine, and C double bond N is known as imine. Imine, right? So these are the different systems of tautomerism. Now, there is one more concept by the name called a new thing is hydrogen bonding. Basically, we saw what do you mean by hydrogen bonding? Hydrogen bonding is nothing else but it is a simple force of attraction. It is a simple force of attraction between an hydrogen atom, force of attraction between an hydrogen atom which is directly linked to an electronegative atom. Hydrogen atom, force of attraction between an hydrogen atom which is directly linked to a electronegative atom to another electronegative atom. I'll don't get confused. Force of attraction between an hydrogen atom which is linked or which is attached to an electronegative element. To be more precise, suppose if I say X, element X, where X will be oxygen or nitrogen, right? Or you can say even fluorine, oxy or nitrogen and fluorine. So hydrogen atom attached to an hydrogen atom attached to an electronegative atom with another electronegative element X, which is also where X is equal to either oxygen or nitrogen or fluorine. I'll see hydrogen which is attached to an oxygen which is an electronegative element, and no doubt this is water, or you can say this is water, right? This is water. Suppose, or I will write in a straight HOH, water. Fine. Just wait a minute. Right. Now hydrogen is bonded to an electronegative element oxygen. Right. Now this same hydrogen, suppose if is bonded to another oxygen. This is hydrogen, right, and this is another. So this is H2O, this is water, and this is H2O, which is water. Here oxygen, two water molecules in which the oxygen element is attached to the hydrogen which is attached to another electronegative element. Just try to understand. So this is the force of attraction. This is the force of attraction between hydrogen which is attached to an electronegative element with another electronegative element. Fine. So this happens to be a hydrogen bonding. I'll write it in short form HB. Hydrogen bonding. Fine. Another, this hydrogen will be attached to OH. So this also is a hydrogen bonding. Fine. Like that. So two water molecules. That means they are same molecules. The bond, force of attraction between the hydrogen and oxygen of the same type of molecule, is it? Same type of molecule. This attraction can also happen between two different molecules. Also. Take for example HOH. Fine. And this can be bonded to HNN. Right? And this is another H. So this is NH3, which is ammonia. Oxygen which is bonded to H. X is ONF, I have told you. This is H. This is water. This is ammonia. So between the same molecule, between two different molecules. Fine. Or you can also take, suppose if I write C double bond OOH acid, suppose, and this is hydroxide OH. So the force of attraction between this O and the ortho position where there is the OH. That means I will say ortho position, two ortho positions are there. So this ortho position is OH and the first position is carboxylic acid. Okay? So this is also hydrogen bonding. This is also hydrogen, but this is within the same molecule. This is within the same molecule. This is between two molecules. Two molecules, both the molecules can be same or both molecules can be different. This is different and this is same. This is within the same molecule. So such type of hydrogen bonding are known as intramolecular hydrogen bonding. And these type of molecules are known as intermolecular hydrogen bonding. So intermolecular hydrogen bonding and intramolecular hydrogen bonding. Intramolecular means within the same molecule, and intermolecular means within the molecules, two molecules who are of same type or of different types. Fine. This is known as intramolecular and this is known as intermolecular. So two types of hydrogen bonding we have seen. Fine. Yeah. So another type of intramolecular example I'll give you. Same example of a diketone type I will say. Suppose C, this is an O, this is an H, this is, take for example, CH2 dash C double bond O CH3. Suppose now here within the same molecule, sorry, CH double bond, suppose if I take this, now this imaginary force of attraction between this is within the same molecule, this is between the same molecules, right? So you can say this is 1 2 3 diketone types, 1,3 diketone, right? So this is also known as intramolecular hydrogen bonding. Strength of hydrogen bonding. Strength of hydrogen bonding. Now the strength of the hydrogen bonding depends upon the electronegativity of that element X, or you can say the electronegative element. Strength of hydrogen bonding, you can say, is directly proportional to the electronegativity of X, of which X is equal to, either O or N or F. Right? Electronegativity. More the electronegativity, more the hydrogen bonding. For example, I'll say as we have studied in the lower classes, that as we go from left to right of the periodic table, the electronegativity value increases. This, take for example, from left to right, if this is boron, carbon, nitrogen, oxygen and fluorine. That means nitrogen, I can say it is less electronegative, this is more, and this is the most. So this fluorine will give me a stronger hydrogen bonding as compared to oxygen, and oxygen will give me a stronger hydrogen bonding as compared to nitrogen. Fine. I'll give you an example. Take for example, and take for example Obviously this is a stronger hydrogen bonding, and this is a weak hydrogen bonding. Fine. Or we can also say it as strength of hydrogen bonding is inversely proportional to plus I effect or plus inductive effect, because inductive effect means electron donating group, plus I effect. So make it is it's important. Strength of hydrogen bonding is inversely proportional to the plus I effect, and it is directly proportional to the electronegative or the minus I effect, whatever. Take for instance primary, secondary and tertiary carbon atoms to which the OH is attached, to which the H is attached, to be more precise, to which the electronegative element and H is attached. I'll give you an example for it. Take for an instance CH3, CH2, CH2, we can say CH2OH. Fine. This we can say CH3, CH2, CH2, CH2OH. And this we can say CH3, CH3, cancel all this full part. After this, yeah, if it completely cancel this part. Now we will see, take for example 5 carbon atoms, OH. This is a primary carbon atom. Now this is a secondary carbon atom. This is a tertiary carbon atom. Fine. So primary, secondary and tertiary. So I can say this primary carbon atom will be having a stronger hydrogen bonding as compared to secondary, should be more as compared to tertiary, because the electron donating groups of tertiary carbon atom will be much stronger as compared to secondary, which is as compared to, because there are 3 CS3 groups are attached. 3 CS3 groups are attached. Right? 3 CS3 are directly attached to this carbon atom, which is attached to OH group. So this is 3 there. Fine. So now we'll go with the next topic. If after completing this structural isomerism, if you see the another part of isomerism is known as stereoisomerism. Basically, what do you mean by stereoisomerism? Stereoisomerism is nothing else but compounds having same molecular formula. Compounds having same molecular formula but different structural formula. Same molecular formula but different structural formula. So, but they differ in the properties. Having the same molecular formula but different structural formula, but they differ in their properties. Why? Because due to the arrangement of atoms in space, the molecular formula remains the same, the structural formula also remains the same, but only the position of atoms in space changes. Right? Position of atoms in space changes. Take for instance, see, if I say COOH, if I say H if I say like that, and sorry, suppose like that I say, just a second. This is Cl. Suppose if I take a, you can say the same molecule, but if it has a COH, suppose this is carbon, I will say this is hydrogen, this is hydrogen, and this happens to be chlorine. So the molecular formula is same, the structural formula also is same, but only the arrangement of atoms is different. Here the carbon carboxylic acid, which was the bond was going down, which was below, it's going down the plane, dotted bonds, and this is a solid bond, so it is coming towards the plane. The bonds has changed, the position of the bond has changed, that means the position of the atoms has changed. So such type of isomerism is known as stereoisomerism, and such type of isomers are known as stereoisomers. Okay? Now in case in these type, in stereoisomers, basically what happens, there is that they differ only in some properties, some physical properties, in some physical properties, some physical and some chemical properties. Not all, very, means we can say it has the nearly same physical properties and the chemical properties, right? So that is known as stereoisomerism. Now we will see in stereoisomerism, basically speaking, in, you can say, stereoisomers. In stereoisomers, you have conformational isomers. Conformational isomerism. You have conformational isomers. Second one is configurational isomer, conformational isomer, configurational isomer, and the third type is known as geometrical isomers. Geometrical isomer. Geometrical isomerism is also known as cis trans isomers, right? Stereoisomers are conformational isomer, configurational isomer, and geometrical isomers, which are also known as cis trans isomers. So we will see conformational isomerism. Conformational isomers is, they are interconvertible isomers. Interconvertible isomers. Why they are interconvertible? Because the interconvertibility of these isomers is due to the rotation along the C single bond C. Interconvertible means they can be converted from one isomer to the other isomer. Interconvertible isomer due to rotation along the C single bond C sigma bond. Sigma bond. C single bond C is known as sigma bond. As I have told you previously, take for example, I will say hydrogen, this can say take also hydrogen, this is hydrogen. Take for instance, suppose if I say now this this is also hydrogen, this is hydrogen, and this is. Now if I say that there is a along the CC single bond, suppose this part remains same, I will hold this part and the other part I will rotate it, right? Then it can so happen, if I rotate it, this can go here, right? It goes here, then this hydrogen atom can come here, and this, right? So there is a complete rotation along the 6cc bond. Not compulsory that the rotation has to be completely 180 degree. It can be a slight amount of rotation also. It can be. Take for example, I'll give you. Suppose this is hydrogen. This is hydrogen. With this solid bond which was here, it can be just rotated to this much angle, and so this accordingly this will change, and accordingly this will change. So this also is a conformational isomerism because it is a rotation along the C single bond C, right? Yeah. Now, second one is configurational isomerism. Configurational isomerism or configurational isomers. Now, what do you mean by configurational isomerism? As in case of conformational isomerism, they were interconvertible. Means once it has rotated, again it can come back to the original structure. In configurational isomerism, what happens? They are non-interconvertible, means they cannot be converted. They cannot be converted. Why? Because there is no rotation. There is no rotation along the CC single bonds. There can be no rotation along the CC single bonds, sigma bonds. Therefore, if there is no rotation, then obviously there does not come the issue of interconvertibility. Does not come any interconvertibility. That means you can say isomers that are not interconvertible. Due to no rotation along the sigma bond. Since there is no rotation along the sigma bond, obviously if there is no rotation, then no formation of any interconvertible isomers. So then why it is known as isomers? Configuration. See, one thing it is sure, it is the arrangement of these atoms in space, no doubt about it. The arrangement of these atoms in space. Take for example, I will take hydrogen, right? This is CH3. This is, take for example, ethyl. Et is ethyl, and chlorine. Suppose if I take the mirror image. Suppose this is a mirror. If I take the mirror image, what will happen? The mirror image will be exactly same. Right? See here, and then this will be 80. So this and this. Suppose this is A, this is B. If I pick up structure B as such and try to place it on A, pick up from here and place it on A, what will happen? The H will be seen here, the chlorine will be seen here, and ethyl will be seen here, right? That means they have same molecular formula, same molecular formula, same structural formula, same structural form, but differ in arrangement of these atoms. And the mirror image, it has a I can say it is a non-superimposable mirror image. Right? Superimpose means it should sit one upon each other. One upon other is known as superimposable. Non-superimposable mirror image. Although it is a mirror image, but it can't match with this compound exactly in terms of bonds. So it is a mismatch of this. So it is a non-superimposable mirror image. The non-superimposable mirror image isomers are known as enantiomers. Enantiomers. What do you mean by enantiomers? Enantiomers are non-superimposable mirror image. Non-superimposable mirror image of a particular isomer. Non-superimposable mirror images of a particular isomer are known as enantiomer. So enantiomer are also a part of configurational isomers. So it is not rotation along the CC bond. It is not rotation along the CC bond. It is just a simple mirror image. The mirror image gives you non-superimposed, therefore these are known as enantiomers. Now, another part of configurational isomers is diastereomers. Diastereomers. Now, what do you mean by diastereomers? As this was non-superimposable mirror image, diastereomers will be non-superimposable and non-mirror image. Means it will not be a mirror image, neither it will be superimposable. For molecular formula will be same, everything it will be same. Everything it will be same. Molecular formula will be the same, structural formula also everything will be, but they will be non-superimposable. For example, H, OH, COH, if I take the same thing, OH, COH, C, take for example, this will be OH and H. So these two are not mirror images, they are not the mirror images, right? No mirror image. Neither it is superimposable, obviously it will not be superimposable. So non-superimposable, non-fluorine. This is known as tartaric acid. Tartaric acid. Tartaric acid, right? So it is non-superimposable, non-mirror image. Tartaric acid. So you have understood enantiomer, you have understood diastereomers. Fine. Now, the another part is geometrical isomerism. Or you can also say cis trans isomers, and the phenomenon is known as isomerism. Why? So cis trans. Now, what do you mean by this? These are also isomers which are non-convertible. Means they are not interconvertible. You mean to say the isomers which are not interconvertible. But why they are not interconvertible? As in the previous case, they were interconvertible due to the along the CC single bond. Right? In the first case we have seen. Now this is not interconvertible due to there is no rotation along the CC double bonds or pi bonds. There it was sigma bonds, here it is pi bonds, double bonds. Right? That means, that are not interconvertible. They are which are not interconvertible. Why? Due to, you can say, restricted rotation along the pi bonds or double bonds. Pi bonds or double bonds. The pi bond does not mean always C double bond C. It can be C double bond N also, or it can be N double bond N, or also it can be, means along the pi bonds, double bonds only. Pi bonds, in this case only double bonds. Don't take triple bonds. Pi bonds, because triple bonds also can be considered as a pi bond. So C double bond C, C double bond N, or N double bond N, whatever. But precisely we generally see C double bond C. For example, we will take suppose this is H, this is CH3. Take for example, this is CH3 and this is H. We can say this is 1, 2. So this is 2, 1, 2, 3, 4. 2 butene, we can say. Fine. Take for example, this is A. And take the another molecule. Same thing, C double bond C. Here it is H. Here it is CH3. And just rotate the position of this. This is the, will change the position of this. So due to this, no. So this is also 2 butene, but only the position of this methyl has been replaced by H, and H has been replaced by CS3 in this case, right? Right? Okay. Don't be under the consideration that since double bond has been rotated, so H has gone to CS. No, there is no rotation. Only the position of methyl groups we have changed here, and H. So such type of isomerism in structure A, here we can say similar groups are present on same side of double bond or the pi bonds. Such type of isomers are known as cis isomer. Similar groups, it's a compulsion कि similar groups have to be there, and that too not on the same carbon atom, should be on the adjacent carbon atom. Similar groups on the adjacent carbon atoms, if they are on the same side of the double bond. Once again I'll say you, two similar groups if they are on the same side of the adjacent carbon atom, same side of the, to be more precise, same side of the double bond which are attached to the adjacent carbon atom, right? Two similar groups attached to a carbon atom, adjacent carbon atoms, attached by a, these adjacent carbon atoms are attached by a double bond. So such type of isomers are known as cis isomer. In this case, the similar groups are attached on the opposite side, right? Don't on the opposite side, not on these same carbon atom. Once again I am saying, not on the same carbon atom, but on opposite carbon atom, I mean on the adjacent carbon atom. So this is known as trans isomer. Trans isomer is what? Opposite side. Side of pi bond. Right? So this is now known as trans isomer. Okay, I think so we have done, it's done for this lecture, and you might now come to a conclusion of this complete isomerism part. complete isomerism part. This is the basic isomerism which I have taught you, and this will be very helpful for your henceforth topics, right? So I hope that you might have understood till now. So if any issue or any question, you can just write to me on my email ID, or on you can do also a WhatsApp to me, right? Plus be thorough with all my previous lectures and try to connect all the lectures, because each lecture it's directly, if you see a middle lecture, take for example, if you see a seventh lecture, lecture number 7, without seeing the previous lecture 6, you'll not be able to understand. So it has to be in a single flow up till now. So just look after all the lectures, and then you'll be able to, yeah. So it's my attempt to make you thorough with the basic organic chemistry, so that it can be helpful for you in the future. I hope you might have understood, right? So I will take a leave now. Thanks for the lecture, to attend the whole lecture. I'm very thankful to you. Okay. So once again, I'll request you to please do like my video and subscribe it, and do share it, right? Okay. Thank you. Thanks a lot. Namaskar.